You are okay, good. I actually did one of your own words. I've never had one. But this is all the time. She's like, actually, she said it was she definitely said that. She definitely said that. It wasn't good. Actually, I just did something to it. I just put that sugar. Good. Was that everything?
I'm just going to pass around the sign machine. I already get started. That way I don't forget to pass around the sign machine. I'm notorious about that. Just the announcement, I wanted to start with the announcements on the board. For those that have not already come to my office and seen me, quiz 1 and quiz 2 is due today. I will be in my office. I will either be in my office or the department office, which is on that second floor where all the glass windows are, across from the labs. I'll either be in one of those two places today until 1:30. So just get it to me today. Originally, I said I'll be here from 3:30 to 4, and I need to know if anybody, or 2:30 to 4. No, yes. Is anybody going to come see me between 2:30 and 4 today? Okay, then I'm not going to be here from 2:30 to 4. But since I said I would, I wanted to double check and before I determine what to. So quiz 1 and 2 are due today. I will be posting your homework over the material we covered Tuesday and today, from Tuesday and from today, sometime between 9:30 and 1:30. I will also post quiz 3 and 4. All of that, I believe, is due by Monday night at 11:50. No, yes, no. The homework's due Monday night by 11:59 p.m. and if I recall, the quizzes are due on Tuesday by 11:59 p.m. The quizzes are much shorter than the homeworks. They're usually 5, no more than 10 problems. So they're usually pretty quick to do. The homework's going to take a little bit more time. I will also go into the textbook and figure out what optional homework is valid for chapter 13 and post those homework problems. Now, last time I went ahead and posted the answer key, but since then I've gotten in answer key manuals, the solutions manuals. And so instead of posting the answer keys, I have 2 copies of the solutions manual. One will be found over in the library where you can check it out and check your work. And one is going to be found in my office. And as long as I'm in my office, you can come grab it and sit out in the hallway and check your work. we're gonna try it that way and see how it goes. And then I'll decide what to do next. So any questions about the announcements? The lab for Monday is the Alkene lab. It's going to be our first wet lab. If you do not have goggles, you'll need to get goggles. Now, I will be able to sell goggles because I'm the UCA ACS chapter advisor, so I can keep some and sell them as needed. So if you need goggles, I will be able to sell you some goggles. UCA ACS takes Cash App and credit card and or debit card, I should say, and cash. So it's $7 for the goggles that UCA ACS has. Any questions for me? Okay, if not, we're going to get into the chemical reactions today, which for me is where the chemistry really gets to be a lot more fun, is when we start talking about the chemical reactions. And these chemical reactions are the same reactions that you're going to see in biological systems. So that is because biological molecules are simply bigger organic molecules. So a lot of the things that we'll be discussing starting today is going to be stuff that we'll use on and off throughout the semester. More so than naming of alkenes and alkynes and naming of alkanes. What we are starting today is going to be something that you're more likely to see throughout the rest of the time. So this first section just is describing types of reactions. We're not going to get into detail about a specific reaction. We're just going to describe some of the types of reactions that you typically see for organic reactions. And they fall into 4 categories. The first category is an addition reaction. And basically, it's adding something. In this case, it's adding something to the double bond. Now, it can be something that is homogeneous, such as H2 or Cl2 or Br2, but it can also be heterogeneous, such as HCl, HBr, or water. All it means is if it's an addition reaction, we are adding something across the double bond. Just like the term says for elimination reactions, if you're dealing with an elimination reaction, you're eliminating something to make a double bond. So we add addition reactions, you're adding to the double bond. Elimination reactions, you're eliminating something to make a double bond. Any questions about the general types of reactions, the first 2 general types of reactions? We're going to see examples of the addition reactions with alkenes today. Not so much elimination reactions yet, but we will see addition reactions. And I'm letting people catch up to my writing because I understand that I started out ahead of you a little bit today. Okay. The next type of reaction is called a substitution reaction. And you've actually already seen a substitution reaction when we talked about the halogenation of a alkane. Basically, you're going to substitute a hydrogen, typically, for another element. Or a halide, a halogen for another element. So up here, I've given you a couple of examples. Again, we've already seen the first one. The first one was in chapter 12, when we were working with alkanes, where we would take the alkane and we would substitute onto it a halogen, typically chlorine or bromine. This other type is going to come up when we start dealing with ether formations. We'll see it when we start dealing with ester formations or amide formations. And that is, we're going to take something that is, we can take one compound and add a salt of some sort, a salt being something that it contains a cation. And we can substitute the halogen in this particular case for what the portion that was attached to the cation. And in this particular one, that means we make an ether, which is a methylpropyl ether. So again, substitution, just like the term states, it's substituting one substituent with another. Substitution reactions are actually quite common in protein chain formations. The last type we're going to talk about in the general form is a rearrangement reaction. Typically, this involves the rearrangement of a double bond. Rearrangement reactions are actually quite common when we start talking about aldehyde formations from an alcohol, or carboxylic acid formations from an alcohol. So rearrangement is another form. Now, as was pointed out here, they are isomers of one another because they're going to have the exact same molecular formula. But they are going to have a different arrangement. From one another. So this first section, you're not really, other than knowing, being able to recognize whether it's an addition reaction, elimination reaction, a rearrangement, or a substitution, I'm not really asking you for details. There's not going to be a whole lot of problems associated with this. It is the next part where we get into utilizing one of these basic types of reactions that we're going to start to see problems on an exam. So, alkenes. Addition reactions of alkenes. There are 3 objectives for this section. The first is probably going to be the most challenging of the objectives, because you are going to learn to predict the products of a chemical reaction, given only their reactants and or in a catalyst. Or you may be asked, okay, what are you adding to the reaction to go from this reactant to this product? Now, with respect to alkenes, there's going to be 4 types of addition reactions we're going to talk about. The first is going to be hydrogenation, which, as you will see when we get into actually looking at hydrogenation, it contains the word hydrogen in the name. So in other words, you're adding hydrogen across a double bond. The next one is halogenation. Well, it has the term halogen, so it means you're adding a halogen across the double bond. The next type of addition reaction is called a hydrohalogenation, meaning you're adding a hydrogen and a halogen across the double bond. And the last one is one way that we can create alcohols is called hydration. And what is hydration normally? Water. That's what we're doing, is we're adding water across the double bond. Now, as part of this, you're going to identify whether something is unsymmetrically substituted or symmetrically substituted. And to be quite honest, that concept is quite easy. Because if you're adding hydrogen or chlorine, you're going to have a symmetric substitution, because you're going to add the exact same thing to both sides of the bond. But when we add hydrochloric acid or hydrobromic acid, or when we add water to the double bond, now you're going to have an unsymmetrical substitution, because you're adding 2 different types of things to the double bond. Now, it's this unsymmetrically substituted substitution that has to utilize Markovnikov's rule. And we'll discuss Markovnikov's rule in more detail, but basically, or you'll actually see it in a little bit. Markovnikov's rule says that the hydrogen has to go on the carbon with the most hydrogens.
Now, if you have equal opportunity, that's when we get a racemic mixture, or that's when we start to get mixtures, which is challenging to separate. So let's just start looking at these. Hydrogenation. Is the addition of hydrogen across a double bond. Now, hydrogenation, if you simply add hydrogen, nothing is going to happen. If you just add the hydrogen, nothing is going to happen. Hydrogen by itself does not have enough power to break a double bond. In order to break that double bond and add a hydrogen across the double bond, you got to have a catalyst. And the most common type of catalyst is going to be a metal catalyst, such as palladium or platinum or something of that nature. But you got to have a catalyst. So, how would I discuss this type of reaction on a test? Let me let you catch up with writing it, and then I'll discuss how you might see this type of problem on an exam. Don't worry, we are going to do some examples here in a few. Okay, this type of problem can be asked in a couple of different ways. I could give you the reactants and the fact that you need a catalyst. And you would have to give me the result of the reaction. That's one possible way that this could be asked. I can give you the reactants and you have to give me the product. Another possible way that this could be asked is I can give you the reactant and I can give you the product, and you would have to give me the rest. So those are two ways that this can be asked. And we'll look at those a little bit more. But basically what you got to remember is double bond and you get two hydrogens, then you had to have hydrogen in a catalyst. Hydrogen in a catalyst puts hydrogens on the double bond. That's all it does. Okay, the next one that is a addition reaction. Again, you have to remember, alkenes will only do addition. Keep that in mind. That will help you in predicting things. Alkenes can only do addition. Now, halogenation. If you look, it has the word halogen in it, so it has to be something that is dealing with group 17. Technically, I could add iodine, but it's typically we're talking chlorine and bromine for biological systems, so that's the ones we focus on. But if we're talking about a halogenation, we're adding a halogen to the double bond. Again, it's an addition reaction. Always remember, alkenes only do addition reactions. And what I'm describing for alkenes is true for alkynes as well. What I'm describing for alkenes is good for alkynes as well. We just have to have double the quantities. So, halogenation, if I add chlorine, I'm going to add a chlorine to each carbon that was in the double bond. Or if I add bromine, I'm going to add bromine to each carbon that was in the double bond. Now, this last reaction is a very, very useful reaction. Because it's something that when we're in the laboratory, we can use to test if we have an alkene present. The reason we can test to see if we have an alkene present is because bromine is this reddish brown liquid. Whereas once that bromine is added to the double bond in the halogenation reaction, you wind up with a clear liquid. So it goes from red to clear, but only if it had a double bond that it can go across, that it can add to. This same reaction is also good for determining the level of unsaturation. You add a drop, it goes clear. You add another drop, it goes clear. You add a third drop, it stays brown. Well, we had to add 2 drops. So that tells us something about the level of unsaturated double bonds. Whereas if I have to add 10 drops for it to go reddish brown, then that solution is a lot more unsaturated because I had to add a lot more bromine to make it change colors. Okay. There we go, that's better. Hydrohalongenation has hydro to indicate a hydrogen and halogenation to indicate that you are going to add a halogen. So you're adding a hydrogen and a halogen. Because we're adding two different elements, we are going to get an unsymmetrical substitution. Because we are adding two different elements, we're going to get an unsymmetrical substitution. So it's important to know, okay, where is the hydrogen going to go then? And where is the halogen going to go in the reaction? And that is where Markovnikov's rule comes into play. Markovnikov's rule allows us to determine where the hydrogen is going to go and where the halogen is going to go. Because the hydrogen will always go on the carbon with the most hydrogens. So if I take this 2-methyl-1-propene, and I add hydrobromic acid to it. To figure out where the hydrogen goes, I'm looking at the carbons in the double bonds. And I'm asking which one has the most hydrogens. Since the CH2 had the most hydrogen present, that is where the other hydrogen is going to go. So, you have your double bond between these two carbons. According to Markovnikov's rule, the hydrogen has to go on the carbon with the most hydrogens. I have two hydrogens here. I have none on that carbon. So since this one has the most hydrogens, that's where the hydrogen must go from the HBr. The Br then goes on the other carbon.
So the one, like what it says attached to the carbon with the most hydrogens, it's the carbons that are on the double bond.
Correct. You're only looking at what's on the double bond. Now, organic chemistry, though, we have, remember, there's like 20 billion organic molecules. There's a lot of options here. So you can have alkenes that have the same number of hydrogens on the two carbons. An example would be this compound, which is 2-pentene. If you look at the double bond, there is one hydrogen on one of the carbons, and there is one hydrogen on the other carbon. So they have the exact same number of hydrogens on the carbons that make up the double bond. So when we add HBr, where's the hydrogen going to go? Well, that's when you can get a mixture of compounds, and you actually have to show all of them. So, since they have the same number of hydrogens, you can place the hydrogen on the left carbon and the bromine on the right. And you would get 2-bromopentane. But if they have since they have the same number of hydrogens on both of the carbons making up the double bond, we can also place the hydrogen, on the right-hand carbon. And if you place the hydrogen on the right-hand carbon, then the bromine winds up on the left-hand carbon and you get 3 bromopentane. So you follow Markovnikov's rule. The hydrogen goes on the carbon with the most hydrogens. But if you have equal opportunity, that means you're going to have a mixture.
So will you want us to write it like that in the condensed format and only show the hydrogens on the double bond area? Or will you want us to write it all the way up?
You only have to, you can mimic what is up here and just add the new bonds.
Okay.
I think that answered your question.
Yeah.
Sorry, so the answer is both of these structures.
Yes, the answer is both of the structures.
Follow question. Will you take off if we
You'll-
don't do both of them?
You'll only get half credit. I do partial credit where possible. But in this case, if you only gave me one of the structures, you would only get half credit for the answer.
That's the point of that, was to show both.
Correct. Other questions? Again, it's all because you have unsymmetrical substitution. The same thing occurs, I never finished out my writing, so I'm going to start writing now. The same thing occurs with hydration. Hydration is the addition of water to an alkene. So you have your alkene, and we're going to add a water molecule. First of all, this reaction by itself will not occur. This reaction by itself does not occur. Water is not strong enough to add to the double bond of an alkene or alkyne, or a triple bond of an alkyne. You have to have a catalyst. And the catalyst in this particular case, and I wanted to make it generic, is an acid catalyst. So our options for acid catalysts could be H2SO4. That's the most common one, is adding some sulfuric acid to the mix. But you could technically probably add HClO4, which is a strong acid. You could add nitric acid, but you got to have an acid catalyst. And once you have an acid catalyst, then you're going to take this molecule and you're going to have an OH and an H that attaches. Again, the most common one, but I don't want you to get stuck on it. The most common one is sulfuric acid, but I don't want you to get completely stuck on sulfuric acid because it can be another acid. Now, again, this has to follow Markovnikov's rule. So, for example, let's take that same compounds we had before. And if we add water with an acid catalyst, then what we're going to get is that the hydrogen is ultimately going to add to the carbon that had the most hydrogens, and the hydroxide is going to add to the other carbon.
So they will stay together, they'll split apart.
The water splits apart to make OH and H. That's why if you look at the top reaction, the generic reaction, you'll see I circled H separate from the OH, is because they split apart. You, again, because this is an unsymmetrical addition, you can get mixtures if the carbons have the same number of hydrogens. Questions? I have a few people that are looking perplexed, so I'm. Okay. Let's look at some reactions. Let's get a little bit of practice with all of this. Write the reaction equation when 2-pentene reacts with HCl. Well, the first thing you got to do is figure out what the reactants are. So we are talking 2-pentene here. The 2 is telling us where the double bond is. It's on the second carbon. So that is CH3, CH, double bond, CH, CH2, CH3. Or you could have written, you could have started with and actually drawn everybody out. So that you can see how many hydrogens are needed on each one. It's whatever works for you. You could have also drawn the line structure. If you do the line structure, one thing I would recommend though is on the double bond, figure out how many hydrogens there are. So for example, right now I see on this carbon right here, I have 3 bonds, so there's 1 hydrogen there. So I would have gone ahead just to make my life easier in the end and showed that hydrogen. Same thing with the other one. I would have gone, okay, this one that's on this double bond has 3 hydrogens, 3 bonds already. So it also has just 1 hydrogen. So, and the reason I'm having to do that is because of the second ingredient, which was HCl. We know that this is going to be unsymmetrical. Addition. We know it has to be an unsymmetrical addition because we're talking about 2 different elements. So that tells us I got to use Markovnikov's rule. Well, in this particular case, using Markovnikov's rule, it does not matter where I put the hydrogen because they had the same number of hydrogens. So the result of this one is going to be 2 products because the carbons of the double bond have the same number of hydrogens. And again, this is unsymmetrical. Addition. All of this writing, you don't have to do all this writing, folks. I'm trying to help you think the way I think through things. So this is showing you step by step my thought process. So I would have drawn that plus that one. Or if you like to do it the other way, you could have done it as CH3, CH, H, CH, Cl, CH2, CH3. Either way would work, however you want to do it. Oh, this is that one, not that one. Let me at least make them the same. Questions? Let's look at another example. Let's look at what alkene could you use to make the following product? Draw the structure of the reactant and tell what other reactants or reagents is also required. So basically, in this particular case, I want to know what I would use to get to this compound. Do you think this is going to be due to hydrogenation, halogenation, hydrohalogenation, or hydration? So it means we're adding water to something. So what are we adding water to? Well, we know that means we have to add a double bond, right? So where's the double bond going to go? The fact is it just has to go where the OH is, because this is a ring structure. So it could be that. Everything would be named the same. Now, is this sufficient, that what I have written out, is that sufficient with it being hydration? You got to have your acid catalyst. This would have been the answer that it is looking for. Let's look at another example. I figured this is more helpful than anything, walking through thought processes. 2, 2, 3, 3 tetra bromo pentane can be prepared by an addition reaction of excess bromine with an alkyne. Draw the structure of the alkyne. So in this particular case, it gave us a product. And the first thing you should do is draw out the product. So it's CH3, CBr, Br. There's the 2,2. CBr, Br. There's the 3,3. CH2, CH3. There's your pentane. We know that it is the result of adding excess bromine to an alkyne. We want to know, what is the alkyne? Well, we added Br2. So let's back it up. If I were to do this and I would take away a Br2, I would take one from one and one from the other so that I had CH3, CBr, double bond, CBr, CH2, CH3. That would be if I'd have only had one Br2. But it said I had an excess of Br2. So the alkyne would be CH3, C, triple bond C, CH2, CH3, because I would remove another Br from the equation. So this excess basically is telling me to remove all Brs to get to the alkyne. Let's look at one more example. 1 pentyne reacts with HBr in a 1-to-1 ratio. To yield two different addition products. Both products are bromopentenes. And have the formula C5H9Br. Draw the two products. Okay, start with, what does one pentine look like? Well, it's CH triple bond, C, CH2, CH2, CH3. Or if you rather draw it out so you can see it better, so you can see all your bonds. The first carbon can only have one hydrogen in order to have a triple bond, so that it only has 4. The next carbon in line can't have any hydrogens because of the fact that it has to be attached to the CH2. And then we continue with the CH2, CH3. Did I get what you needed? Okay. Whichever way you want to write it out is fine. You got to be used to looking at both. Now, to this, we are adding an HBr, but there was something very important in the statement, and that it was in a 1-to-1 ratio. So we're only adding one HBr to one pentine. To get two products. So the first product that we get when we follow Markovnikov's rule is that we'll get 2 hydrogens followed by the carbon, and it will have a CH2, CH3, 2 CH3 on it, and it'll also have a bromine on it.
So they can interchange like that? Like you start with the alkyne and then the products go to alkenes?
Yes, because alkenes and alkynes both undergo addition reactions. I just showed you with the alkenes. But you can start with an alkyne instead. And if you're only adding one, you can only break one bond. And so that's why you can get to the alkene. What's the other product? Bless you. The only other products that I can come up with has the bromine on top, because remember, a double bond is rigid. You can't rotate around a double bond. They're still the same product, but there isn't any other option not in follow Markovnikov's rule. Have a feeling they screwed up on this particular question in the textbook.
So you can't rotate it around the bond, but if it's a single bond.
Single bonds can rotate, so they're the same no matter what. Questions? Okay. Let's see, what time is it? 9:06. We are just going to quickly start into the discussion of aromatics. We'll really pick up on aromatics on Tuesday and finish up our discussion of aromatics. I will be going in, and the other thing I need to do is update next week's folder to reflect what I expect us to go through. So things are getting kind of, I'm having to update what I had already put together for the semester because of snow and ice and all of that jazz. Oh well, going with the flow, going with the flow. I have to remind myself. So if you'll recall, we talked about what an aromatic was. An aromatic compound has 3 double bonds. Technically, this is in resonance with the same structure where the double bonds are rotated. So a lot of times we will show it as a circle inside because those double bonds, they're in constant motion inside. It's not really a double bond. It's more spread out among the entire thing. This is referred to as a benzene ring. They are flat molecules consisting of three double bonds. Now, because it has double bonds, the first expectation is that, oh, I can do addition reactions. But the thing is, benzene does not do addition reactions. Like the typical alkenes. That is because of the aromatic ring stabilizes the double bonds. So what we're going to do is we're going to talk about on Tuesday, we'll start with talking about how to name aromatic compounds, because they are named different than alkenes are. And then we'll get into the reactions that aromatic compounds will actually undergo. Questions, comments, or concerns for me over the material we covered today? The main thing we covered today was there are 4 types of chemical reactions for organic compounds. Addition, substitution, elimination, and what? Hydration. No, that's the type of reaction. Rearrangement. Those are the general umbrellas. Alkenes, though, they only undergo one of those, and that's the addition. And so I spent most of my time on those additions for alkenes. We're going to get into aromatic compounds on Tuesday of next week, and what we're going to find out is aromatic compounds only do substitution. So that's why understanding that big umbrella is important, because then you can remember, oh, these only do addition, these only do substitution. So it gives you an idea of what type of reactions they should do. So questions, comments, or concerns?
With the material learned today, are you on the exam, would you be testing for like comprehension and content, or like?
It would be a lot like the problem I was doing at the end. So other than recognizing the type of reactions, it will be more about being able to come up with what is the products of this reaction, or what reactants would I have started with to perform this type of reaction. They will not be in word format so much, as I will draw out the reactant and ask you for the products, or vice versa. Other questions? Yes.
Is this what homework 3 is going to be over?
Homework 3 will be over what we went over on Tuesday and what we went over today.
Oh.
So it'll be over naming alkenes, alkynes, as well as the reactions of alkenes, alkynes. That will be the big umbrella. There's some other little things like properties of alkenes, alkynes that we went over, but I think the big things were naming and then the reactions. Other questions, comments, concerns? The quizzes, quiz 3 and quiz 4, one will probably be over what we went over Tuesday, and one will probably be over what we went over today. And that should catch us up so that we're not behind on all of our various pieces of things due to the snow. think the quizzes are due next Tuesday. Because usually there's either an exam or a quiz due on Tuesday. So, except for quiz 1 and quiz 2, which I gave you a long grace period.
Would they be on active or would they be pencil, paper, and class?
Pencil, paper, and class would be your exams. Okay, folks, I will sit here and answer other questions, but otherwise I will see you on Monday for lab. Oh, thank you.
I know. Yeah.
So do you need that doctor's?
I normally don't.
Yeah.
because the quizzes are on active.
Yeah,
And then I will record the lectures so you can watch it, and if you have questions that arise as you're watching the lecture, then you can. Oh.
Yes.
As soon as I can leave here and go upstairs, I'll do that.
I'm just gonna wait for you, so I don't
Okay.
look, leave and come back.